A very good afternoon, dear participants. Today we are going to deal with another technique of separation, which is specialized for volatile molecule, that is gas chromatography. And you are familiar with Dr. Vandana. She took your session yesterday for HPLC, and she will take the session again today for gas chromatography and some detection techniques. So I again welcome Dr. Vandana here today to deliver her talk on gas chromatography. Now I will hand over the virtual dais to Dr. Vandana. Over to you, Vandana.
Good morning, everyone. Thank you, sir. So today we are going to study about the gas chromatography, which is also a chromatographic technique, as we have studied last day about the HPLC. So, like HPLC, like different type of chromatographic techniques, GC is also a separation technique. Sorry, there is some problem, I think.
Your PPT was disappearing.
Is it visible now?
Yes, it is visible.
Okay. So today we are going to study about the gas chromatography, which is also a type of chromatographic technique, and generally it's used to separate the analytes which are volatile. So, as we have studied last day also, like the basic principle of any chromatographic technique is the partition coefficient or distribution coefficient. How a certain analyte or solute is better soluble or have better interaction with one solvent rather than the other solvent. And based on based on this property, we separate the particles or samples. So sorry. Um, so based on this separation, we separate the different. Sorry for the interruption. Actually, someone has came. So based on this separation of a analyte, distribution of an analyte in a particular solute, we separate that analyte. And most of the chromatographic techniques that are used in present day, like we have studied last year also, we use a mobile phase and a stationary phase. So based on the chromatographic technique has been divided into several categories, as we have discussed last year also. And based on the mobile phase, it can be divided into the liquid chromatography or gas chromatography. And based on the various kind of interaction a analyte have with the stationary phase, it can be divided into different kind, like adsorption, partition, ion exchange, and size exclusion. Similarly, based on the dimensionality of the column, it can be divided into either two-dimensional or three-dimensional. So basically, the GC gas chromatography is a chromatographic technique where the mobile phase is used is gas, so it is a gas chromatography. The mechanism involved for the separation of analyte is the partition or distribution coefficient, so it's a partition chromatography. And the column is a column chromatography because column is used for the separation, so it's a three-dimensional chromatography. So basically, gas chromatography technique has the stationary phase, which can be liquid or can be solid. However, the mobile phase is always gaseous, that is gas. So the stationary phase, in case of the liquid, the how can we call a liquid a stationary phase? Actually, what happens, we immobilize a particular kind of liquid that should have a certain specificity for the separation on a support material, like immobilize it on a support material so that it become stationary. And in case, so such kind of gas chromatography is called gas liquid chromatography, where the mobile phase is gaseous and a stationary phase is liquid, a liquid that is immobilized on a solid support. So gas chromatography can be gas solid chromatography also, where the stationary phase is used is solid. However, the gas solid chromatography is very less common. It's not common, and it's generally used to separate the less molecular weight gaseous gases like hydrogen sulfide and etc. They have very less sensitivity and they're not generally used to separate the analyte. Most of the time we use the gas liquid chromatography. So there are certain restrictions for the type of analytes for which we can use the gas chromatography, like the analyte which has to be analyzed through gas chromatography must be thermally stable, like it should be stable at high temperature, and it must be volatile. And because we use analyte in a vapor phase for the analysis, so it should withstand high temperature. And if it is semi volatile or not volatile, like it's liquid or solid, it has the property to get volatilized through a process called derivatization, where we use the certain chemical to add certain functional group to the analyte so that it become volatile at certain temperature, and so we can get the vapor phase of this analyte. what is the separation mechanism? As we have I have said in the earlier slide, like it's a partition chromatography. So the separation is mainly based on the absorption of this or solubility of this analyte with the stationary phase, as well as the volatility of the compound. So the more volatile is the compound, it will pass through the column more faster, and less soluble, it will also move faster through the column. So actually the separation depend on the how strongly, basically the all kind of chromatography is based on the interaction of this analyte with the stationary phase and mobile phase. So in this case also, the how the analyte, which is generally in the vaporized state, is how strongly it is getting interacted with the stationary phase. Based on that, they will leave the column, and based on it, because different component will have different degree of interaction, so different component of a sample will leave the column at different time point, and that's how they will get separated. Now once the component of the analyte gets eluted from a column, they must hit some detector, so that the signal that is coming from the column, it should be detected. So detection is also based on the different principles, which we will discuss later, and detectors are also either mass dependent or concentration dependent. Mass dependent means it identifies the compound based on the mass, or concentration based, it means it shows the concentration of the analyte. So now we will see the general principle of the gas chromatography. This is the overall diagrammatic representation of how a gas chromatogram looks like and what are their components. So as we have discussed in earlier slide also, the most important thing in gas chromatography is the mobile phase, because here the gases are used as a carrier gas, which is nothing but a carrier to carry the sample, which is vaporized through the column, so that it gets separated, and then can be detected through the detector. So first we will come to the gases. So what kind of gases are used in the gas chromatography? Generally, there are certain criteria for choosing a particular gas. The gas should be inert, it should be stable, it should be thermally stable, it should be chemically inert, and it should be not that much expensive, and we can get it in a pure form. So most of the times the gas that is used as a carrier or mobile phase is either nitrogen, helium, or sometimes hydrogen is also used. However, the hydrogen is generally avoided because it is combustible, and it has the chances to interact with the unsaturated hydrocarbons component of the analyte, and so hydrogen is generally used. It can be used, but it's not optimum. It is generally avoided. And in case of nitrogen is also very cheap, inexpensive, and commonly available. However, nitrogen is also generally avoided because nitrogen generally produces the less sensitivity. So most optimum gas that is used as mobile phase or carrier is helium, which is an inert gas, and inert gas, and we can get it in pure form. So this gas is that is carrier is stored in a gas cylinder, and these are strongly built cylinders, so that at certain pressure gas is stored in these cylinders, and through this there is a pump, a control unit to control the flow of or pressure of this carrier gas, and also there is a trap which are molecular sieves through which this carrier gas pass, so that if there is any impurities are present, they can get trapped in this molecular sieve. So the purity of this carrier gas is also very important in GC, because this impurity is not only interfere with the separation of our analyte through this column, but it also can interfere with the detection system, because detector may give the signal for certain impurities, and then it can be difficult for us to differentiate the signal between actual analyte and whether it is coming for the impurity. So basically it will increase the noise and increase the baseline. So once this is the carrier gas part. So now we come to the sample injection port. So this carrier gas is mixed with the sample which are in the volatile stage. So this sample can be gaseous, can be liquid, or can be solid also, but they have the property of volatility. They should have the property of volatility. So this sample injection port is of different types. Like it can be manual, it can be auto sampler, or in case of manual also, or auto sampler also, there are different type. Like it can be split injector, non-split injectors, or the sample can be directly also injected into the column. So these different things we'll discuss later also, but here we can briefly summarize it. Like in case of the if we are split injector is nothing but a injector where the part of the sample which only part of the sample is loaded on the column, rest of this is went to the waste. So this split column is generally used for higher sensitivity, and however it only been used when we are confident of the concentration of our analyte, because in that only part of the sample is getting injected. So the concentration of our analyte should be sufficient in that sample. And another kind of this injector is the where the this is part where the sample is injected in non-split injector, uh, where the whole sample is injected into this sampler. And such kind of injection is generally done with our concentration of analyte is low, and if the analyte concentration is high, we should dilute our analyte so that there should not be overcrowding or overloading of the sample. And the sample, certain kind of samples can also be directly injected through the microsyringe using a port in this column. So what is this feature of the injection port? Generally this injection port at very high temperature, more than 20-30 degrees Celsius, than the least volatile component of our sample mixture. Like, because we need every analyte in a vapor state, so the temperature of the injection port, we should keep it 20 or 30 degree higher than the analyte which has the least volatility, so that also can be get converted into the vapor state. So this is the main requirement of this sample port or auto sampler. In case of manual, the things are done manually. However, in case of auto sampler, these are all automatic, where we keep our sample in a particular chamber, and there are micro syringe which automatically take the required amount of sample and inject into the sample port. Once this sample gets vaporized and it mixed with this carrier gas, it will then be injected in the column. Now column is the very important part of the GC system, because because this is the part where the actual separation takes place. So basically, the GCs are generally uh, GCs, this column are generally used in a GC system are capillary column. However, there are different kind of like packed column also. But now, but nowadays, most of the time the column used is the capillary column, which is the more efficient, give high resolution and better separation. And the column length that is used is can be 15 meter to up to the 100 meter, based on what we want in our separation. Like if we want to separate very high resolution, like we want to separate trans fatty acid, we have to use up to 100 meters of this column length. However, we want very crude separation, like we only want to see a fatty acid profile of our lipid, we can use a smaller column length also, like 15 to 20 meters. Now this column is actually the inner chemistry of this column is like this, where the on a solid support system, like it outside this column is made of the either glass, plastic or stainless steel, and from the inner side, like you can see there is a support material like might be the diatomaceous earth or something like that, which is very inert, which provide a good surface area and can absorb the liquid mobile phase very nicely. So so actually, sorry, liquid stationary phase very nicely. So in this case, the stationary phase is liquid which is immobilized over a solid support, and mobile phase is, as we know, it's a gas. So the different kind of analytes will interact with this stationary phase, and this liquid stationary phase has the property of dissolution. Like this analyte, these analytes should have differential dissolution in this stationary liquid immobilized stationary phase. So based on the dissolution or solvation of this analyte particle, and also their boiling point or their volatility, they are get separated. Now we will see like how this their volatility and their solubility result in the differential separation. So to maintain the vaporized state of this our sample and gases, the column is maintained at very high temperature, like up to 300 degrees Celsius. So this column is basically kept in an oven, which whose temperature is very high. So this sample which are injected in this column, so the different analyte must have different volatility or have different boiling point. So and also they have differential solubility in this liquid stationary phase. So obviously the analyte which has very high solubility in this liquid stage will leave this stationary phase very slowly. However, the analyte which have the least solubility in this liquid stationary phase, we will leave this column or move through the column faster. Similarly, the analyte which is very high in a very high boiling point, it means they are least volatile. They will also leave the column very slowly. However, highly volatile compound will move faster through this column. So so the separated analyte which are leaving this column, what we get first? We will get that analyte first out of this column which is coming out, which have the least solubility in this liquid stationary phase and have most volatility. So the first compound that comes out from this column will have the least solubility and most volatility, and so it will hit the detector at certain time, and that time will be is called it retention time. Retention time actually the what is up to what time a analyte is retained in this column. So the molecule which have very less retention time is moving through the column very fast, and they comes out first from the column. So they have the least solubility and most volatility. So based on this retention time, we can identify the different compound or different analytes in our sample. Now this and this is the Carl elution time. This is the dead time actually, because it will take time to get analyte, even the analyte with the least solubility or most volatility also, it will take time to get separated. So first the mobile phase means carrier gas will come out of this solution, this phase, this sorry column. So there will be a delay in the getting the first peak of our first analyte. So this time is called dead time, and this is the different time point, that is the retention time, that at which we will get the different analyte. So how will then we, if now we will get a chromatogram, these detectors will detect these analytes. There are certain type of different kind of detector. Here we have shown the MS detector. This is the mass spectrometry based detector. This is an additional technique which is generally nowadays coupled with the either gas chromatography or the HPLC. There are other type of detectors also instead of mass detector, like electrochemical detector and other photo flame detectors, etc. And these different kind of detectors are also chosen based on the property of that analyte. So these detectors will detect this analytes coming from this column, and we will get this chromatogram. So now once we get the chromatogram, and we are getting the different peaks at different retention time, then how we will be sure that this peak is of that particular analyte. So for that we generally run a mixture of standard are nothing but the mixture of known compound whose retention time we have known, and identity of that compounds are also known. So based on that we calculate, we make a calibration curve with our known compounds and their known concentration and their retention time, and based on that comparing our chromatogram with our known standards, we can identify these components. And this identification process nowadays is mostly done automatically in a software, where there are libraries of different compounds uh, based on their retention time, and so they automatically software matches our peak with that library, and then it gives the list of identified compounds. So this is the based on the retention time we identify the compound. Then how we will know the what is the concentration of our analyte in the sample. To know the concentration, basically it depends on that is the area of the peak. How much more is the area, and this area is proportional to the how many times a particular analyze is hitting the detector. So the wider the area means, or a higher the peak means, the means is the higher concentration of the analyte is present. And to know the concentrate of our concentration of our analyte, we first calculate the area, then we compare it with the calibration curve that we prepare using the mix of standard which has run through this system under the same condition as we were our samples. So the concentration of the standards that are run in the same condition, that can be matched through a calibration curve through this area, and in this way we can identify the unknown component and also quantify them. So this is the basic principle of the gas chromatography. Now we will discuss the all of these portions one by one. So there is certain limitation of the for the what kind of analytes can be analyzed in a gas chromatography, because the most important property for an analyte to get analyzed in gas chromatography is its volatility. So all the compounds which are volatile at the temperature that they are volatile are not stable. So that kind of compound cannot be analyzed through the gas chromatography. Generally, the what we analyze through gas chromatography are organic compounds, uh, which are volatile below the 4 degrees Celsius, 400 degrees Celsius of the temperature. They should have very high thermal stability. They should not decompose at such a high temperature. They have the molecular weight within the moderate range, because very high molecular weight again interfere with the volatility. They have the volatility, higher the molecular weight, they have issues with the volatility. So because of these limitations, only about 20% of the non-organic compounds can be analyzed through gas chromatography system. Now, however, the concentration range that can be detected through GC can be of the even parts per million to parts per billion range. So, what kind of analytes are not suitable for GC gas chromatography? So, the analyte definitely which are thermally labile, means they decompose at very high temperature, cannot be separated through this gas chromatography system. Very high molecular weight compound, because they have the low volatility, so they are also very difficult to get separated through this system. Very trace amount, which are very minute quantities, like in parts per trillion or like that, they are also very difficult to get analyzed through the GC system. And 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 one more thing, like active analytes, because in this case the we are volatilizing the compound, so and they are getting adsorbed on the stationary phase, so they are completely broken down. So the active compound, which we need to be in an active state, like proteins or peptide, they can't be analyzed through this gas chromatographic system. This is the GC instrument, how a GC instrument looks like in the normal lab setup. So this is the sample loading tray. Actually, this is all the automated process where in these tubes we keep our samples, and this is the syringe loading compartment, where the micro syringe that are generally quartz needles are fitted, and they robotically, like automatically, they plunge into this sample loading vials, and take the required amount of sample, and all of these settings are made in a software, in a computer software, and according to that setting it operates. So it automatically keep this take this sample, and then it will be mixed through the carrier gas, and then this is the oven part, this is the oven where the high temperature is maintained, and in this oven the capillary columns are kept, and this column part, at very high temperature, this separation is takes place, and from this the data goes to the detector, and this is the control panel through which the different parameters are controlled, like pressure and time of injection volume and everything, like temperature, everything. Another thing is that, like, one thing I forgot, I think, is very important in this part, like to separate the analyte. This we do the temperature programming, like temperature of this oven can be changed over time to get our to get separated our analyte of interest. Like if certain component of our sample which has very less volatility or very high boiling point, then we can adjust the and so they will be going through the column very slowly, and they are very they exit the column very late. So they so in that case we can change the temperature of this oven, like increase the oven temperature so that they can move through the column faster. They become volatile and reach the detector so that we can get the data for that component also. So temperature programming is very important, and temperature programming is done in this oven, where the temperature can be adjusted at various ranges depending upon the analyte, what is our analyte of interest and what we want. So these are the different component of the GC system. As we have discussed earlier, the carrier gas, where in this case of GC, we generally use helium as a carrier gas, though nitrogen and hydrogen can also be used, but they are not generally used because of certain disadvantages. So helium is generally used as a carrier gas, and what properties they should have, like they should be inert, they should generate sufficient detector response, and they should have combustion properties also, like it is needed in certain detectors, like when we use the flame detectors. Second is the injector chamber that we have discussed earlier. So actually the injector chamber diagrammatically we have represented here, and it looks like this, where this is a rubber septum, and this is outer wall which is made of the metal blocks to generate the high temperature so that the this sample can be get vaporized, and the inner line of this injection port is made of glass, which provide an inert environment for our sample, and there is a carrier gas inlet through which the carrier gas, which is kept in the gas tanks, will move inside this injector port, and this is a vaporization chamber where in an inert environment the sample is heated at certain temperature so that it get vaporized, and then the mixed this carrier the sample which is in the vapor state and is mixed with the carrier gas is then loaded on the column. So, as we have also briefly discussed, like injection of the sample can be split or non-split. So, this is the split outlet. So, in case of split injection, only part of the so how this sample is loaded? Actually, the sample is loaded from this region where the micro syringe are generally is passed through this rubber septum, like this they are pierce this septum, and they are the samples are loaded in this chamber, and in this chamber, and then if we are using the split injector, then only part of the sample is loaded and rest of this is moved out to the atmosphere. So this split injection is generally used and is when the sample concentration or the concentration of analyte is sufficient in our sample, so that the very minute quantity of sample is needed for loading on the column for its further analysis, and split column because it needs very small sample, they have better resolution also. However, the injection can be splitless also when the components the components which are which have the analytes which are very less concentration, and we can't afford to lose our sample. We use the splitless injection. And also the sample can be uploaded on this column also directly. So in this case also micro syringes are used, and in certain cases that samples which have the which are in the vapor stage can be directly loaded into this column. So this is the whole injection port, and the temperature of this column is maintained at the 50 degrees Celsius, uh, about 50 degrees Celsius, or 30 to 50 degrees Celsius higher than the analyte which has the least volatility, so that the analyte which has least volatility can also be vaporized. So this is the overall representation of what a injector chamber looks like. Now we will come to the column part. So columns are of also different type, like they are packed columns or capillary columns. So what is the packed column? The packed column is actually have they are not open columns, like the tubing is packed with the tubing that is outside, it's made of either plastic, glass, or stainless steel, is packed with a small inert spherical support material that might be the diatomaceous earth, and on this inert spherical support, the liquid mobile phase might be immobilized, might be liquid, or maybe in case of the gas solid chromatography, solid stationary phase is present on this spherical support. This packed column has certain advantages, like they have very high sample capacity, like very high amount of sample can be loaded on this columns, but they are generally less efficient, and so the poor resolution, as they have very high inner diameter of around the range of 1.5 mm to 6 mm, and generally they are used for the preparative work rather than the analytical use. So next we will discuss is capillary column. Capillary columns are actually have very thin inner diameter, and they need very small sample amount, so they're very efficient and very high in resolution. So generally the capillary columns that are used in the this gas chromatography, is from outside it's made of the glass or plastic or stainless steel for to give it a robustness, and then the inner portion of this is it has a solid support material, and on which the liquid stationary phase is immobilized. So this capillary columns are also of different kind, like wall coated open tubular, support coated open tubular, and porous layer open tubular. We will discuss all these three kind of capillary columns later. So basically the capillary columns have very small inner diameter, like 0.1 to 0.2 mm. They can be of very wide range of length, like from 10 meters to 105 meters, and this length of the capillary column is chosen based on our our purpose of analysis, like we want very high resolution and very sensitive analysis, then we can use very large very long capillary columns up to the 100 or 105 meters, like in case of when we are analyzing the trans fatty acids. And if we are using the crude analysis, or we are generally saying common components or major components of a mixture, we can use a smaller capillary length also. Generally, the stationary phase that is immobilized on this capillary columns have the thickness of 0.25 mm. As we have seen that they have better resolution, very high efficiency, and better peak separation as compared to the packed column. However, as the sample amount that can be loaded on these capillary columns are very less, so they have very low capacity. So generally they are used for the analytical purpose. Now we will see like how columns the GC columns looks like in a cross section. So this is a cross section of typical GC column, and there are like a type of column. There's a wide range of columns that can be used in a GC system, and in this here we are only seeing a typical, like most commonly used GC column. So in this case we can see that outer part of this column is made of the polyimide coating, which is very strong and robust, providing it very high strength. And on this fused silica is used as a support material, and over this support material the stationary phase is immobilized in the form of a film. So the stationary phase generally used in this case are either polysiloxane, polyethylene glycol, or silicone phases. All are these liquid mobile phases. They are very inert. As we know, this mobile phase also have certain property, like they should have very high boiling point. They should not vaporize at the temperature that is generally used in the oven or capillary. They should be chemically inert, and they should be thermally stable. They should not decompose at very high temperature. So these are the material which have this property, so they are used as a stationary phase in these columns. So generally that most efficient column that is used are Scott columns, W Cott columns, that is the wall coated open tubular column. And this is the example of the wall coated open tubular column. Open tubular means it's not stuffed, like they are open, and they are tubular, and their wall is the stationary phase is immobilized on a wall of this support material. That is why it is called wall coated open tubular column, W Cott, and they are most widely used columns in the GC system, and they are most efficient as well. Now another type of column is the support coated open tubular column. This is only minute difference from this W Cott column, where the mobile phase is immobilized on a support particles, like that maybe the diatomaceous earth or something like that, and the mobile phase is immobilized on this support column. Generally among these W Cott and S Cott columns, W Cott are more efficient, so they are preferred as compared to with respect to the S Cott column. Sorry. So another type of this column is the porous layer open tubular column. These are also open and they are tubular, and they have this a porous material as a support column and on which the liquid stationary phase is immobilized. Generally, in case of the porous column, stationary phase used is the styrene, aluminum oxide, or molecular sieves. So most commonly used GC columns are this double quad column. Mm, they have, as they are capillary columns, so they have very less internal id. They are coated outside with polyamide coating, so they're very strong, and and they are very thin, so that give them the property that they can be wound into coils. So a very large long length of the capillary column can be used in the GC system. As we have seen earlier slide also, like the length of the capillary column that can be used in GC system is anything between 10 meters to 105 meters. So now what are the detectors are used in the GC system? The detectors that are used should have the certain properties, like for the should have the certain properties like they have better selectivity, better sensitivity, and better dynamic range. Like better selectivity means if the compound which has the similar properties are hitting the detector, then the detector should be able to differentiate between them. So it should differentiate between two compound which are of the which one is the analyte, one is not or analyte, but have similar properties. Then they should differentiate between the analyte and other compounds so that it can be better detected. Second most important thing for a detector is its sensitivity. What is the sensitivity? Sensitivity is how efficiently a detector is detecting an analyte, and the minimum quantity of analyte that can be detected through a detector, minimum the quantity, better will be its sensitivity. Dynamic range is as the detection changes with the change in the concentration of analyte. So the range of the concentration uh, up to which a detector can detect a particular analyte is varies from detector to detector, and it varies between the minimum amount of compound that can be detected and the highest amount of the compound where the detector reaches to the saturation. So based on this range of the detector dynamic range of the analyte concentration which can be detected by detector, there is a dynamic range, and for a better detector this dynamic range should be linear and should be high. The range should be very broad. So actually the GCs can be used in the versatility of the GC, and their wide application is also due to the wide range of detectors that can be attached to the GC system, which have various sensitivity, various selectivity, and wide and linear dynamic range. And that's why the GCs can be attached to a detector which has sensitivity up to the range of the pico to femto to the better resolution of the data. So what a ideal detector should have what properties a ideal detector should have. So an ideal detector should show the reproducible response to change in on analyte concentration. Like it should not if we are analyzing the same analyte repeated time, it should show the same signal. then it should have a linear dynamic range, means the concentration of the analyte which it can detect should be the linearly varies, and it should be large dynamic range, like large range of very wide range of concentration of analytes can be detected through these detectors. Now, these detectors can be either mass sensitive or concentration sensitive, depending on what output they are giving. They are giving the mass or they are giving the concentration. Most of the mass sensitive this detectors should have the low noise, because if the noise will increase, then the peaks or then the signals coming from the analyte which has very less signal will merge into that noise, and they can't be differentiated, and they should be highly sensitive to the analyte, like they should have the ability to detect the analyte at a minimum concentration. Now, these are the different kind of analytes, which sorry, detectors, which are used in the GC system, and how they respond to the to the respond to the analyte, whether they are destructive, they destroy the sample, what is their range, what is their limit of detection, and and whether they are universal or selective, like they can selectively detect a certain analyte or can be universally used. So based on these properties, there are various type of detectors that can be connected to the GC system, and like first is the flame ionization detector. In this detector, basically the sample is is combustible, or in a they are combusted in a hydrogen flame, and then ions are generated, and these ions are then moved through a electric field, and as they move through the electric field, change in their conductivity is recorded as the signal. So as the analyte is destroyed, is combusted in this detector, this is a sorry, destructive type of detector, and they respond to the mass of the analyte. So the response characteristic is mass, and their limit of detection is the picogram range. They can detect 1 picogram of analyte per second. Now the thermal conductivity detectors, they are based on the change in the thermal conductivity of the analyte, and they are concentration dependent, and they can, the lower limit that can be detected through these detectors are around 500 picograms per ml. Similarly, the electron capture detectors, these electron capture detectors work on the principle, like they uh, how uh, the analyte absorbs the beta rays, or from coming from a radioactive source, and generally it is used to analyze the pesticide residues in the sample, and they are actually selective detectors, and they are concentration based, and their limit of detection is very high, up to the 5 femtogram per second. This nitrogen phosphorus detectors are generally used for the compounds containing nitrogen or phosphorus. They are selective detectors. Similarly, flame photometric detectors are also selective. Another one is the mass spectrometry. This is very important, that can be used universally as well as the selectively. We will discuss it later in elaboration, and they give the additional resolution to the GC system. So, and another one is the atomic emission detector. This also are universal as well as the selective. They respond to the mass, and their range is around 0.1 to 1 nanogram to 1 picogram per second. So how the analysis is being done in a GC system? Like as we have earlier seen that once we reach this analyte reach the detector, they will generate a then chromatogram, and chromatogram will how it typically look like. It's like this. Looks like this, which we get the peaks. Actually it will this is the typical chromatogram, where this is the retention time, and this is the peaks, and these are the baseline. And so based on the retention time we can identify the different analytes, and based on their height or their area, the concentration of these analyte can be known. So now, so actually, to quantify the component of a sample, quantify means know its concentration. It is directly proportional to its area in the chromatogram, like area of that peak. If the detector response is equivalent for all the analytes, because if detector is not uniform, then we can't compare. So so generally this peak which we get in a chromatogram is generally sharp peaks like this when we are using the capillary columns, and they are generally triangle shaped or wider peaks when you are using the packed column, because they have not that much of resolution. So but in generally in GC system we use the capillary column. So uh, so if we are using a packed column, we get the peak of triangle shape, and if we are using the capillary column, then we will get the straight line peaks, very sharp peaks, so showing their better resolution. So generally the this is what we do. We measure the this area of this peak, and then the peak area of the all the components are measured and divided by this the peak area, that is the measure of the concentration of that analyte, and it is divided by the whole area, and then it is multiplied by 100 to get the percentage concentration of that analyte in our sample. So this is what we do exactly. Like this is the peak. If we are getting this kind of peak, then this is the peak area, and peak area is calculated using this formula, where this is the peak height is multiplied by the by the half of the peak width. So we will get the peak area, which is proportional to the concentration of our analyte. And before this calculation, the analyte, the peak that we are getting in the GC system should be edited. Like there might be several artifacts. Like always the signal or chromatogram we get from the GC is not ideal. There are several artifacts. Like there may be, though this chromatogram that I am showing you as an example is an close to ideal chromatogram, so there are not many artifacts, but still there is some tilting of this peak. They are not very, some of the peaks are not very sharp, or they are not reaching the baseline, so the quantification of this peak will be a problem. So ideal peaks should reach this baseline should be a straight line, and peaks should be very sharp and a straight line kind. So in general, when we are getting the chromatogram, it must have, like we will see in the later slide. In this slide also we will see what are the artifacts of. So if we are not getting a good chromatogram or ideal chromatogram, which most of the time the case, then what we have to do, the editing. Like all of this editing is done through a software that is inbuilt in the system, so that the solvent peaks which we are getting because of the solvent can be removed, or the peaks that we are getting through the impurities can be removed, so they cannot interfere with our analyte detection or their quantification. Now the each peak is identify their relative retention time, and this retention time is very peculiar for a particular analyte, and there is already libraries available for different analyte for their particular retention time, and we match this retention time of our analyte with those libraries, and then on that basis we identify our compound or analyte of interest. uh, Sorry. Area of each peak is calculated. The area, as we have discussed, is calculated to calculate to know the concentration of our analyte. The area of each peak is then divided by the total area of the all the peaks and multiplied by 100 to get the percentage concentration of that analyte in our sample. So that is how the analysis is done, and generally it's not manual, it's all software based and it is inbuilt. So we just have to set the parameters and they will automatically calculate the identify and calculate the concentration of our analyte. So this is what a standard GC chromatogram looks like. So here these peaks are, this is the retention time, and based on that these peaks are of different analytes, like different compound from like phenol, aniline, nitrobenzene, benzyl alcohol. So based on the this retention time they are matched with the library, and thus they are identified. So this chromatograph is very close to ideal and very good for the identification of the analyte. However, there is a problem, some problem with the quantification of the compound, because in this case we are seeing that there is slight widening of the peak, meaning not with that much of resolution, and that these peaks are not touching the baseline. So though it's close to ideal, but it's still there have some problem and problem particularly with the quantification of this chromatogram or analytes. So as we have discussed, like all the time we don't get a ideal chromatogram. There are several artifacts happen, and this non-ideal or some poor chromatogram that we get in our analysis is due to the several factors, and actually the whole process is need to be optimized for our particular sample or analyte, so that it can be every parameter can be set and optimized according to our analyte of interest, and we can get a better chromatogram. Generally that the artifacts that we associated with a bad chromatogram are due to the carrier gas flow rate. If there is a problem with the flow rate of the gas, or due to the column length and internal diameter, like that also we have to optimize according to the analyte or sample, like which is the optimum length and internal diameter of the column, like for very better resolution or very sensitive and very analytes which are very in trace amounts, generally the column length is used is very high, and so this parameter has to be optimized for our analyte of interest. Similarly, the temperature programming is also affect our end result or chromatogram, so that should also be optimized, and we have to adjust the temperature of the oven according to our requirement to get the better separation and resolution and get the ideal chromatogram. Thickness of stationary phase also one factor which has to be optimized, and generally this optimization process is done through by running some standards or compounds which has the which has the known parameters, and then checking it and along with our sample, so that the different parameters can be optimized for the better resolution. Sample volume also be optimized. We can't overload the column, that will not lead to the better separation and less resolution. So generally in that case, to avoid the overloading, split injections are used. So these are the some chromatogram which are showing some artifacts. Like this is very ideal chromatogram because they are showing very straight line, sharp peaks. Their baseline is very near to a straight line, and they are well differentiated peaks. However, in this case, as we see that these peaks are not well resolved. Like these of two peaks are mixed. These peaks are not reaching the bottom line or the baseline, and baseline is also not very straight. So and then peaks are wider, meaning they are not better result. This is not a good chromatogram. So what actually happens generally in a practical scenario like this is where here we are seeing that baseline is continuously increasing, means the baseline, that is the solvent we are using have some impurities or carrier gas, or the phase that we are using, the sample have certain impurities. That's why we are not getting this clear and straight line baseline. And in this case we can see that this baseline is though near to the linear, but they are very noisy. Like they are very small peaks there. So this indicates the background room noise. Means either the detector is detecting the solvent molecules or certain impurities or something like that. So this background noise is very high in this case, and this will interfere with the differentiation or identification of peaks which are very small, because they will merge in this noise. So it's not good for the better resolution or identification of identification of the or analyte. So to avoid these artifacts, we have to optimize, as we have discussed, all of these parameters as per our analyte or sample requirement. And for that we have to run standard and along with our sample at a few time, and optimize the parameter before the final run. What are the some practical aspect that we have to keep in mind before going for the GCMS? First thing that we have to keep in mind and is whether our analyte or sample is volatile or not, or whether it is thermally stable or not. Second thing is that whether the if our analyte is not volatile, semi-volatile, whether it can be derivatized or suitable for derivatization, so that it can be changed into volatile form. And generally the derivatization process is a chemical modification process. Like for the fatty acid methyl ester, they are converted into the methyl esters, and then it becomes volatile, and it can be vaporized at the higher temperature and can be separated. So generally the purpose of this derivatization is to convert it into high molecular compounds into low molecular weight into non-polar derivative. So in this case, in the case of the lipids, they are first hydrolyzed and then they are trans-esterified using the boron trifluoride. They are esterifying agents, and or they can be silylation can be done for hydroxyl and amino compound like phenols. And these are the some derivatization process that are used, which are generally done in the with the sample before running the GC, so that it can become volatile or can be vaporized at a higher temperature in the injection port or in the capillary column. second thing is that the chemicals which are used in the column, like support material or the liquid phase, should be a very of high thermal stability and should be chemical inert. It should not react with or analyte, and it should withstand very high temperature. The presence of corrosive element in the sample should be avoided, and for that's why the purification of the sample before the GC process is also very important, because otherwise it will damage our capillary system column. And before running the GC, column need to be conditioned and activated, because the columns are generally have the liquid phase which are inert or immobile and highly thermally stable, but it's not always the case. Sometime at higher temperature they will show some sample bleeding, like they may some show reactivity with the or analyte, or they may show some kind of the thermal instability. So columns also can, and this kind of changes in the column is called the column bleed. So avoid this column bleed. What we can do is, before each GC run, column has to be conditioned with our analyte and or mobile phase or carrier gas, and it should be activated before use. And the detector type and sensitivity also should be checked, and it is thoroughly checked to select the optimum detector for our analyte type. Now, what are the application of the GCMS? Generally, the GC is used, have very wide application. They can be used for both qualitative and quantitative analysis with very high sensitivity. They can be used for the environmental analysis, like pesticide analysis in water and vegetable, as well as the vehicle emissions that are gaseous, that can also be analyzed through GC. Clinical medicine like blood, alcohol, drugs, uh, like alcohol component in the blood, drugs, different kind of drugs and their mixtures also can be separated through GC system. In forensic medicine, where whether the explosives or trace compounds are used or not, that can be analyzed through GC. Consumers goods quality control like pharmaceutical or food items can also be analyzed. Fatty acid analysis can be done. Several edible products have flavor component that can also be analyzed through the GC, like what concentration of that component is there present in that edible product, and whether they are within the set limits or not. They can be used for the petrochemicals, like composition of the petrol or solvent purities, like basically the purity of this edible component or petrochemical material or pharmaceutical can be analyzed through applying this GC system. So now we will come to the mass spectroscopy. Actually, the mass spectroscopy is also a detector system, but it's a separate system which analyze the elutant coming from the gas chromatography or SPLC again, so that we get the better resolution. So basically, the mass spectroscopy has these four parts, that are inlet system through which the analyte elutant from the liquid chromatography or gas chromatography come into the mass spectrometry system. There is a source of ionization, because this system need ions. So either electron ionization or other kind of ionization, so that the analytes coming in this system gets ionized. Then different electric field or magnetic fields are used to deflect these ions, so that these ions reach the detector at different angles, and now then this detector detect different component based on that angle, and we get a mass spectroscopy data point, that is a chromatogram. Mass spectrometry graph, and that will be analyzed. So this is the source ionization part, where the ionization takes place, and there will be an electron source, and through this inlet we inject the sample. Then these ionized particles or analytes will pass through this particle accelerator, which accelerate this charged particle to certain velocities. Now then a magnet is used to select the certain velocities, and then they are passed through an analyzer, which are also have combination of electric and magnetic field, and so that the different particles can get separated based on their mass by charge ratio into different components, and then they hit the detector, and detector record the signal. So this is what a mass coupled mass spectrometer, which is coupled to the HPLC system, looks like. Generally, the mass spectroscopy is not directly used to analyze the sample. They are always coupled to either HPLC, liquid chromatography, or gas chromatography. And this analyte, there is an interface between this liquid or gas chromatography and mass spectrometry, where this separated compound through the HPLC or GCE coming separate compound is entered into the mass spectrometer, where they get separated based on their mass by charge ratio, and then they reach the detector, and they get detected, and we get this kind of peaks or chromatogram or mass spectrometry graphs. So what is the basic principle? This I have a generalized diagram for the better understanding of what exactly happens inside a mass spectrometer. So as we have we have discussed earlier, that in mass sorry, in mass spectrometer, ionization is a very important step. In fact, it's the first step. And then these ionized particles are accelerated like to a certain velocity. Then they are passed through a velocity selector. Sorry. And then they are passed, this analyte of certain velocity are passed through a magnetic field to reach the detector, and detector detect the signal in the form of this graph. So what actually the ionization is? So through mass spectrometer we can analyze any of the like gas, liquid, or solid that are coming through HPLC or GC. So in this case, to understand the mechanism, we will take the water as a simplest molecule. So what if we are this water is coming through the GC or HPLC system, the system is reaching the mass spectrometer chamber, where the ionization is taking place. What will happen? Generally, in the ionization chamber, what in general used is the electron source, where very high speed electrons strike this coming molecules, and they knock out the outermost cell electron from the molecule, so that the molecule become positively charged. So if we are taking an example of water, the source electron, which are very of high speed, will target these water molecules either at this bond or that bond. So they will extract out the one electron along with it, so it will become the positively charged. So the molecule that will get is the H2O plus, that is the molecular ion or precursor ion, because it's the main ion. But generally this molecular ion is not stable, it's very unstable. So then it will break into either oxygen ion, hydroxyl ion, or H plus ion. So this fractionation of the molecular ion is called fragmentation. because this is the parent ion, that what is on actual analyte and it's get ionized, so it is the parent ion, and then it is getting fragmented into the components which has different charge. So this is the fragment ion. So every analyte has a certain type of fragmentation pattern that we will see after some time. So once these charged particles are generated that are either parent ion or fragment ion, they will then pass through a accelerator, which is also a part of the mass spectrometry system, which is basically a certain electrodes, positively and negatively charged electrodes, and they are split. So the charged particle through these splits will, obviously they are positively charged, so will move toward the negative charge and they will gain a velocity. So different particles will have different velocity based on their mass, and generally the charge is present is the single charge, because single electron is knocked out. It's very rare that more than one electron is knocked out. So basically the mass is the differential factor. So this accelerator, what it do, that they will accelerate this charge molecule to gain them a velocity. Now this charge particles will reach a velocity selector, where the particles which have the certain velocity can pass through this selector region, and rest of them, like, they are actually have the electric field as well as the has the magnetic field. And these electric, like, this is the sorry electrodes. So this is the direction of the electric field, and there is a magnetic field which is the perpendicular to the direction of this magnetic field. So sorry electric field. So this electric and magnetic field are generally equal in strength. Like here we can say what is the physics. This is the general physics behind this velocity selector component. Like magnetic field and this electric field are equal in nature, and as we know that magnetic field is depend on the charge of the molecules, its velocity and magnetic field strength, whereas the electric field is depend on the charge and electric field strength. So what happens is, if the molecules have the low velocity, it means they are low velocity. That it means they will have the smaller magnetic field, and so they will get deflected towards the electric field. And if they have very high velocity, they will get deflected uh, towards the magnetic field. So based on this velocity, they have deflection towards either the electric field or magnetic field. And the certain compounds which can overcome this deflection can move out this field, and can reach this analyzer part, which is basically a magnetic field. So the charged molecules that are analyte, like in this case of these fragment ions or molecular ion, that is H2 plus, is reaching this analyzer that has the magnetic field. And this magnetic field, because these are charged molecules moving in this field at a certain speed, it will provide a centripetal force to these charged molecules. And the system is such that the magnetic field that this system generate and centripetal force that is applied are equal in nature. So applying the general physics formula, like if q is the charge, v is the velocity, and b is the magnetic field strength, and as we know, the centripetal force is equal to the mv square by r, where r is the radius, v is the velocity, and m is the mass. So v will get cancelled, and we will get the qb is equal to mv by r. Now so r is equal to the the mv by qv. So v is the velocity, and velocity we are certain velocity that we have selected, and b is also magnetic field, which is constant. So v by b is constant. It means this r means the deflection or this angle at which this due to this centrifugal force, this charged particle are getting deflected and they are reaching the detector at the angle, and this angle is actually the proportional to the mass by charge ratio. And generally the ionization does the single ionization, the charge remain also generally constant, so it's proportional to the mass of the animal, sorry, mass of the molecule, mass of the molecule, mass of the either molecular ion or fragment ion. So what this detector is does that it will generate a chromatogram. And uh, and uh, and so though, as we know that different compounds have different molecular weight, so they have different mass, and so based on their molecular weight we can detect the different compound differentially. Based on the height of the peak or height of this peak or signal, it shows the relative abundance of that compound, and so the y-axis will show their abundance, and this will the mass by charge ratio. So like here we are as an example using the water as a molecule, and it's getting ionized into this molecular ion, this fragment ion, and uh, and and so we will expect a spectrum or this chromatogram of having this four kind of peak representing the concentration of these four ions, and they will fall at different points at x-axis depending upon their mass, because r is proportional to mass. So we expect that at this one molecular weight we will get H plus ion at 16 O plus, 17 OH plus, and 18 H2O plus. So generally the this fragmentation pattern, we have taken a very simple example. So this fragmentation pattern is a peculiar to a particular molecule or analyte, and it's actually a signature of that molecule. So the fragmented, like water will have this kind of fragmentation pattern. Similarly other molecules like maybe some amino acid or something like that, they also have a signature fragmentation pattern. They have certain molecular ion and their fragment ion. So based on this fragmentation pattern also, they can be compared with a library of the analyte which already have this fragmentation pattern and their this chromatogram, and which well-known libraries like Sequest or Mascot are present in mass spectrometry library, and they are present in several mass spectrometry raw data analysis softwares. So the fragmentation pattern of these analytes are automatically compared with those libraries when we are doing the software based analysis, because we are just for the simplification, we are to understand the simplify the things and understand the mechanism, we are seeing this manually, but all of these things are done in a software, because this is very simple molecule, but we generally in practical terms are dealing with very complex mixtures like proteins, peptides, or some metabolites, etc. So it's very complex, so they are analyzed in a software system, but the basic principle is same, like the fragmentation pattern or their molecular weight are searched against a library, and based on that the compound is identified. So one thing is more that in mass spectrometry analysis generally we get the peaks for the fragment ion, because molecular ion is very unstable, so generally it decomposes into fragment ion. So the in relative abundance or intensity of the peak for the molecular ion is very less as compared to the fragment ion, or so fragment ion is always present in the more abundance. And now what kind of ionization is used in case of the mass spectrometry system. Generally, the ionization is used, as we have discussed earlier, like high-speed electrons are used as a source of ionization. However, the ionization can be hard ionization as well as the soft ionization. So hard ionization is also can be either electron ionization or chemical ionization. What happens exactly in the electron ionization is electron ionization is actually the high speed electrons are bombarded on our gaseous molecules so that they knock out the outermost cell electrons, and the molecules become the positively charged. Now these positively charged molecules are generally molecular ions, which then get fragment into the fragment ion, as we'll discuss, and this fragment and precursor or molecular ion then enter into the analyzer part, then accelerator and then mass analyzer part, and then they get analyzed, and then they will reach the detector and generate a characteristic peak. Similarly, in case of the chemical, however, in the case of chemical ionization, what we used as certain gases like ammonia or methane are used, which are at very high pressure and temperature, and so at very high temperature, these gaseous molecules gets converted into the radical species. Like they have lone pair of electron, and these radical species are very reactive. Then they will interact or hit upon the gaseous phase molecules, and then they extract out an electron from these molecules, and leading to the development of a positive charged molecular ion and another radical species. So it's kind of chain reaction. So in this case, instead of electrons, we are using the using the gas, like reagent gas, maybe the ammonia or maybe the methane, as a agent to knock out the electron and generate the molecular ion. Now once the molecular ions are generated, then the procedure is same. Like however, in this case, generally the molecular ion is relatively stable as compared to this when electron is used, because here we are using the gases to knock out the electron. However, they still can get fragmented into the fragment ion. Now this fragment ion as well as the molecular ion go into the analyzer part of the mass spectrometry, and then they are get analyzed, and we will get the spectra. Another mechanism that is used in the ionization is the soft ionization, which is used generally for the fragile heat labile molecules. We use the soft ionization, in which the atoms are used to generate the molecular ion, and generally the molecular analyte is adsorbed on a liquid matrix, and then we'll bombard the atoms on that matrix, so that the molecule will become positively charged, and solvent will get evaporated, and we will get the molecular ion. So the soft ionization is used in case of the fragile or heat labile molecules. Now what are the type of generally ionizers which are attached to the mass spectroscopy system? That is the MALDI or the ESI. So what is the MALDI? Basically, the MALDI is the matrix associated laser desorption ionization. It means in MALDI, our molecule of interest are adsorbed on a matrix, and we will give laser to the matrix. Generally this matrix have the are complex molecules. They have aromatic rings. So we will give the laser or energy to this matrix molecule, and they will then resonantly transfer this energy to the our analyte or molecule that we are supposed to analyze through mass spectrometry, and because of this transfer of energy, they become charged. They will leave the electron will be knocked out and they will become charged. So why we will use this kind of ionizer? Because we can why can't we directly hit the molecule? Because this laser are very high energy beam of light, so they can decompose and they can destroy our sample. That's why this resonance transfer method are used. So here the laser light falls on a matrix, and then through matrix the it's transferred to the our analyte. Generally the ratio in which this the our analyte and matrix is of around 1 to 1000, where matrix the concentration is of 1000, and our analyte is concentration is 1. So in this way we will get the molecular ions, and these molecular ions again then analyzed in the same way. They will get fragmented into the fragment ion, then they are analyzed. Generally this MALDI ionizer is attached with the TOF analyzer, that is the time of flight analyzer. Second of the ionizer that is used in the mass spectrometry is the electron spray ionizer, in which the electro spray ionizer, in which the actually the molecule of our interest are uh, coated with a liquid solvent, so that it will become a micro droplet, like a micro droplet, and then they are heated using the this dissolution gas and nebulization gas, like nebulization gas, that is basically the nitrogen, heated nitrogen gas, and so that they will become the charged droplet. And they are passed through this charged tunnel, so that they become a charged droplet. Charge are present outside this, and then the solvent that are coated on this analyte is sample is then evaporated, and due to the evaporation, now the or sample remains, and then it will split into the into different charged particles, and now this charged particle will go to the analyzer part. So this kind of actually an ionization is used in case of the biological sample like peptide or DNA, which are very heat labile and which are very sensitive to the hard ionization. So this kind of ionization is suitable for that kind of molecules. So once the molecules are ionized, they will go to the analyzer part. So to simply describe the analyzer, I have made certain diagrams to discuss the analyzer. This is the simplified portion of the mass spectrometer, where the ionization takes place. Then ions go to the analyzer, and then from here they will go to the detector. So the analyzer which are broadly used are the either quadrupole analyzer or time of flight analyzer. What are the quadrupole analyzer? Quadrupoles actually have these 4 kind of electrodes, which are 2 of in upside down, and 2 are like left and right, so like they are perpendicular to each other and facing each other. So in cross section they will look like this. So what we will that charged particle of various size and various polarity, like negatively and positively charged, depending upon their size, they are larger, smaller, very smaller, they are entering this analyzer part. And in this analyzer part has these electrodes which are either positively or negatively charged, and they are perpendicular to each other. So like this E1, E2, E3, E4, these are 4 electrodes. So what is done is the polarity of these electrodes are getting changed very rapidly. So once, if certain time it is E3, this upside this horizontal electrodes are positively charged, these are negatively charged. Then after some time the orientation change, this becoming negatively charged, these become positively charged. So the ions moving in this tunnel, this is quadrupole, are become very confused. Like if they are these are positive charge, they will obviously go to the negatively negatively charged poles, and if negatively charged pole, they will go to positively charged pole. So this rapid, due to rapid change in orientation, and also the radio frequency is used to generate the vibrational vibration or of the this charged particle. So this due to the rapid change in this polarity, these ions get separated into two separate clumps. Like plus will positively charged will be in one group and negatively one in one group, and they will never mix. So one thing is here done, like the two different kind of charges are getting separated into two different groups. Now the in each kind of charges there are different sizes of molecules, so they based on their mass they has to be separated. So we will use a so uh, so what we will do that we are changing this polarity, and we are pushing it through this tunnel also. So we are using here direct current also. So the mass which are larger in size will be will as we have seen that these charged particles are getting two separate clumps, and now they are since the mass, the particles which has mass, higher mass, will be deflected less with this RF source, and while the particles which has smaller mass which will be deflected more. So actually they will hit upon this analyzer, and they have to travel the longer path. However, smaller weight molecules will deflected less, so will take a smaller path. They will have to travel less distance, so they will reach the detector first as compared to the higher mass. So this kind of analyzer is also called high pass mode, where the higher weight uh, higher molecular weight molecules are leaving the molecules late as compared to the this smaller mass. Similarly, when if we apply a direct current to it, so they will also disturb this charged population, and they will deflect this current will deflect this charged molecules due to the electric forces, and so they will then the charges will try to refocus itself so that it can travel this path to reach the detector, and larger mass are refocused very slowly. However, smaller mass will refocus fast, so they will travel fast, and however they will travel so slow, so the low molecular weight molecule will leave this column first. So this is called low pass mode. So depending upon that variation is in this RF frequency and direct current, they can be operated in different mode like high pass and low pass. This is generalized mechanism. Actual term, there are lot of variations are also present. Another thing is that another type of analyzer that is used in the mass spectrometry is the time of flight analyzer, where the different and generally the TOF analyzer is not suitable for the separating different varieties or different polarities of charge. They are suitable for only a single type of charge, like positively charged molecules. So what in this case is done is that these charged molecules of different sizes are passed through this analyzer, which has the increasing field strength, like as the negative charge is increasing, so they are pushed towards the negatively charged charge, and the molecule, and in this process they will gain a velocity, and they will have a certain kinetic energy. So molecules which are larger in size and also they have they have an electric field applied to these charges. So so the kinetic energy gained by this charges are equal to this field strength, the electric forces, and that the distance that they have to travel. So if we will analyze this equation, we at last we will get this equation where m is equal to 2qes by d square into t square, where s is the distance, d is also the uh, distance of this analyzer, d is the distance of analyzer, qes is that distance that the charge has traveled. So this electric field is constant, d is constant, s is constant, and charge is generally, as we have discussed earlier, that single ionization is generally singly charged in the molecules which are we will get after ionization are singly charged. So it means that mass of the this charged molecule is proportional to the time. So it means the higher the mass will be, time taken to reach the detector will be higher. So based on this, the different mass charge molecule of different mass will hit the detector at different time. So that's why this is called the time of flight analyzer. And as the different charge molecules different time by detector, they will get separated and we will get a chromatograph. So this is the I just tried to simplify the process and try to discuss the basic concept. So this is the overall what we have to cover today in the in the in this lecture. So now now we will I will want to show you a short video, or I think if time permits, Anurag sir will tell.
Yes, yes. Actually.
So so this is the short video of the how plant metabolites are analyzed in a GC system.
Welcome back to Science in Real Life. I'm Molly, and we're at the University of Illinois at Urbana-Champaign with our super special guest, Amy Marshall-Colon, and she's an assistant professor that she studies the chemicals that plants make and break down over the course of their lives. Plants can't run away from stresses in their environment like a drought or a predator eating them or massive student loan debt, so they have to make use of their metabolism to respond to these stresses instead.
And my lab in particular studies how plants respond to low nitrogen nutrition. Nitrogen is one of the most essential elements for plant growth and development. Most of the world's soils have very low nitrogen fertility. Farmers don't have the money available to buy these expensive inorganic fertilizers. So really what we would like to do is to better understand nitrogen uptake and assimilation so that we can figure out how to make plants more efficient at taking up the nitrogen that's available to them. My lab uses a technique called metabolite profiling to help us understand gene function. And metabolites are anything from amino acids to organic acids, fatty acids, lipids, sugars, and the volatiles that you smell if you're smelling a bouquet of flowers.
So plants with two different genotypes might respond to the same stress differently, which would then show up in their metabolite profile.
That's right. And since we're interested in nitrogen metabolism, we profile amino acids because they all have nitrogen molecules in their structure. So today I'm going to show you how to extract amino acid metabolites from plant tissue and then profile them using a gas chromatogram mass spectrometer, or GCMS.
You're probably familiar with GCMS already. It's the machine in crime shows that always saves the day by identifying a weird speck of chemical that ties the murderer to the victim.
So now we're going to extract some amino acids as well as some other metabolites from leaf tissue from 2 different Arabidopsis genotypes. What we're going to do is grab a leaf, a nice big juicy leaf off of these plants, and we're going to put them into these pre-weighed tubes that contain methanol. It's really important when we're quantifying amino acids that we know how much does that sample weigh. So these are 2 different genotypes, and they might have the same amino acids but in different quantities. It's going to take a while for this methanol to extract all of the metabolites from these samples, but this is all of the metabolites that are in that sample, and we're really interested in the amino acids. So we can take it a step further and do what's called a phase separation so that we can separate out different kinds of metabolites based on their chemistry. We're going to add chloroform and water to our sample and methanol. And we're doing that in the hood because chloroform will make you pass out. So now we take our sample and we just shake it up really, really well because what we want to do is extract all of the metabolites from it. We get something like this. So now we're going to just take the top phase, which is the aqueous phase. And this is the one that has the amino acids. So now that we have extracted our aqueous phase, we now need to dry it down to completeness so that we only have those metabolites dried and in the bottom.
So we don't want any liquid left at the end.
No liquid. Okay, so it's going to take about 24 hours to dry them down to completeness.
And now they're ready.
See, they're completely dry in just 24 hours. So now we're going to derivatize these samples, which means to make the metabolites volatile. And volatiles are compounds that have no net charge, which is necessary for us to be able to run them through the GCMS. So I'm going to add a couple of different chemicals, pyridine and MSTFA. Now that the derivatization is over, I transferred them to a vial and we're ready to run them on the GCMS. So first, our samples are going to get injected and enter the GC, which is going to separate out the different metabolites that are in the mix within the sample. Then as those compounds come off of the GC, they're going to enter the MS, but that is going to blow apart each one of these compounds, and the ions from those compounds is going to hit the detector, which will then give us the fingerprint or the signature of each one of these metabolic compounds, and we can figure out who they are.
All right, so this is the data that the GCMS will spit out.
That's right.
Okay.
So these are called chromatograms. And what we see here is the separation of the different metabolites that were in our sample mixes. And so these are the results from 2 different genotypes. And if we just look at the big picture, we can see that they have very similar metabolite profiles. But if we were to overlay these chromatograms and zoom in, what we can see is that there are some distinct differences in the amount of metabolites that are in the 2 different genotypes. If we look at this peak right here, you can see that there's a pretty big difference between this little blue peak and the big gray peak. So it's the same metabolite, in this case it happens to be glutamine, but there's a whole lot more glutamine in the gray genotype than the blue genotype. So results like this are really exciting for us because we can already see that there's a difference between these genotypes, and it likely has something to do with their nitrogen metabolism. And so we can use this information to further look into what genes are driving this molecular phenotype that we've observed through our metabolite profiling.
Oh, that's so cool. So you could potentially figure out if one of those plants is more efficient at using nitrogen, or is better at breaking it down, or something like that.
That's right.
Oh, very cool. Amy, thank you so much for joining us on this episode. We had a great time learning about
So, Dr. Vandana, I think we can take the questions. They are there in chat box.
So this is what I think. If time allows, on if there are any questions, then okay. There are few questions in the chat box. I will. Uh, so I will take one by one. Should I take, sir? Anurag, sir?
Yes, please take.
Okay. So first question is that does retention time of the compound vary with concentration of the sample? Or there? No. Retention time is not depend on the concentration of sample. Retention time is based on it's like interaction of that analyte with the mobile or stationary phase, and its characteristic of a particular analyte. So it's not depend on its concentration. What the concentration denotes is its peak of that peak, the height of that peak or area of that peak. So to know the concentration of a analyte, we have to compare the height or area of the peak, and to identify the compound, we have to compare the retention time with the library of different compounds. So retention time is not depend on the concentration. Which ionizer is better between MALDI and ESI? So in terms of efficiency, I think nowadays the electrospray ionizer is used most of the time, and MALDI is earlier used. So ESI is better than MALDI, I think. But it also depends on the what kind of analysis we are doing. So however, with most of the state-of-the-art GCMS or LCMS systems, generally the ESI is used as a ionization source. I think these two questions are only there in the chat box. So if anyone has any other question, they can ask, or they can write it in chat box right now also.
Participant, you can unmute yourself also to ask the question directly. So I'm not seeing any question in the chat box. I think since this is a new topic for them at all, at graduation level, so they might be absorbing this much content which has been delivered to them.
Sorry.
If there is no more question, then I would ask the host. Okay, thank you, Vandana, for being here with us and delivering this nice talk, and which was very informative. Okay, some question has raised. I was going to end the meeting. Saran is asking, while phase is using inert gas such as helium, then how an elite can have affinity for mobile phase?
In this case, actually, the mobile phase is generally used as a carrier. They don't involved in the affinity or interaction like in case of the liquid chromatography. So they are actually used only as a carrier. So we need not to have any affinity of the analyte with the mobile phase. Generally, the affinity with the stationary phase, which is also liquid, which is mobilized on a solid surface, is what we take into account for the separation. And helium is used as a carrier gas only. It's not interacting with aureolite. So yes, any other solvent can also be used. Other organic solvents are also used, and there are well-defined protocols. So depending upon the type of source material and what kind of components we want to separate, we can use different organic solvent as well to extract the metabolite, because every component is not soluble in the methanol. So 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 methanol is one of the component, but one of the solvent, but the other solvents are also used.
So, any other question, participants? So there are no more questions. So I will again thank you, Dr. Vandana, and yes, Sapna is writing. Thank you so much for this informative and amazing session. Thank you, participant, for your patience and enthusiasm. Now I would ask the host to please end the meeting for all. Thank you.